So in this session, we are going to see about quantum states which is present inside the qubits. Session is going to reveal the theoretical model of qubits explained with quantum states. Quantum states, the quantum building blocks. In quantum mechanics, everything begins with quantum state. A quantum state is a mathematical description that contains all the informations we know about quantum system. You can think of it as the DNA of the quantum entity. So, whenever we are going to think about quantum states, quantum entity is going to play a major role. Quantum numbers. So inside quantum simulators or quantum computers, quantum number is going to play a vital role. So here we are holded with four numerical division like s orbital, p orbital, d orbital, f orbital, etc. The first three defines the orbital designation, and finally the last one defines the spin state of the electron. Quantum number L is the orbital quantum number and defines the type of orbital the electron is in. Quantum number ML is the angular momentum quantum number and it defines the orientation of the orbitals for those that have non-zero angular momentum called non-spherical. Finally, all electrons must be in one of two spin states defined by MS, either in 50 percentage positive flavor of probability and 50 percentage negative probability. Those are the selection rules which defines all possible quantum states of the electron in an atom. So that is the quantum number. Ground state. So ground state of a quantum mechanical system is its stationary state of lowest energy. The energy of the ground state is known as the 0 point energy of the system. An excited state is any state with energy greater than ground state. In quantum field theory, the ground state is usually called the vacuum. So in this depiction, we are holded with energy, excited states and ground states. Energy levels for an electron in an atom, ground state and excited states. So after observing the energies, an electron may jump from ground state to a higher level excited state. So we can't able to measure what the answer is going to be in the quantum computer because of this jumping states. So key concepts in quantum states. First one is termed to be a state vector, which is called to be as an ket. So quantum state is typically represented by a state vector, often denoted as ket, where ket represents the quantum state. This vector encapsulates all the information about the quantum system. Superposition. Quantum states can exist in superpositions, which means they can be a combination of multiple states simultaneously. For example, a quantum bit or qubit can be in a superposition of both 0 and 1 states. So normalization. Quantum states must be normalized, which ensures that sum of probabilities of all possible outcomes equal to 1. This normalization constraint is essential for interpreting the quantum state probabilistically. So operators means quantum tools. So operators in quantum mechanics are like the tools we use to manipulate quantum states. They are mathematical objects that act on quantum states to produce new states. Operators correspond to physical observables such as position, momentum and spin. So key concepts in operators. Hermitian operator. So these are special class of operators that play a crucial role in quantum mechanics. They have a property called hermiticity, which ensures that their eigenvalues are real, making them suitable for measuring the physical quantities, observables. Operators represent observables in quantum mechanics. For instance, the position of the particle is represented by position operator x, while momentum is represented by momentum operator p. Eigenstates and eigenvalues. When an operator acts on a quantum state, it may produce a new state. The new state, if it exists, is an eigenstate of the operator and the corresponding value is eigenvalue. Eigenstates are crucial for measuring the observables. Quantum state or qubit. Let us use qubit example. A qubit is possible in two states, conventional. So this is the representation which determines the amplitudes of measuring the qubit in bracket and one state. So operators in action. So let us say we want to measure this qubit in this basis, means we can use poly Z operator, which is represented in this slide. To do this, the poly Z operator is defined as this, and it is going to yield the answer in terms of the probabilistic measure, which the qubit will collapse to produce the answer in terms of the probabilistic sense. So quantum computing applications. We are going to hold some number of applications in terms of quantum cryptography, security, quantum machine learning, simulations, emulations, and pathology resolution. So quantum crypt is the first application. So this is one sort of applications where quantum computing is going to play a major role, where the keys can't able to be breaked out. So quantum computing implicating the event of breaking the existing cryptographic standards, which is termed to be as a 248-bit RSA. 219 US National Academics of Science reports that unlikely within 10 years, however, these methods will improve. Lattice cryptographic method in terms of complex 3D arrangements of atoms is going to produce the same. So nature's quantum security features. Reality is information theoretic. Computational complexity class of quantum information has access to security features naturally built into quantum mechanical domains. So the principle is it is going to deliver no cloning theorem, no measurement principle, quantum statistics, quantum error corrections, and computational complexity. Killer app, quantum machine learning and quantum computing, statistical methods with probabilistic output. So next one is quantum optical neural networks. So classical neural network architecture and quantum optical neural network architecture. So in classical neural network architecture, which is placed in left side of this depiction, is showing that hidden layers are rectified with linear units, and the output of neurons is going to use the sigmoid activation function to map the output into the range in terms of 0 and 1. So in right side, we are holded with quantum optical neural networks, where you are going to hold the inputs with the single photon Fox stage. The single site nonlinearities are given with Kerr-type interaction, which is applying a phase quadratic equation in number of photons. Readout is going to be given by photon number resolving reductors, which measures the photon number at each output mode. So next is quantum optimization use cases, which is a D-wave systems, which has been used in warehousing setup. So here in this figure, we are holded two sort of examples where 1100 robots with 2050 items in 3 millimeter dimensions, all the instructions are present. Optimization algorithms, which is relevant to quantum, is going to coordinate all the hundreds of robots, which is going to pass within 5 millimeters of each with a speed of 4 meters per second, fulfilling 65,000 orders per week. So Volkswagen 418 taxi network in Belgium is going to deliver the optimized travel time, which is going to implement resulting traffic management systems in Lisbon and beyond. So third example is simulating chemistry. So which is going to conduct 7-qubit superconducting circuits with false color to simulate beryllium hydride molecule, which is IBM providers delivery, which is useful for simulating millions of atoms at present, which needs quantum computing to capture quantum mechanical interactions between electrons. So inside CPU, GPUs, TPUs, and QPUs, GPUs is going to deliver graphics processing unit, which is a 3D graphics card for fast matrix multiplication. TPU is tensor processing unit, flow through matrix multiplications without having to store in trium values in memory. Quantum processing unit is going to deliver a Sycamore 2020, which solves the problems in quadratically or polynomically faster, exploiting SC properties in terms of superposition, in terms of entanglement, in terms of inference. So scalable global quantum networks is going to deliver quantum internet, which is going to deliver security, privacy, and scalability, which is going to deliver some sort of homogeneous scalable qubits, efficient optical interfaces throughout the entire network machines. So next application is in terms of supercomputing processors, which drives quantum nodes with optical electrical interconnects. So two methods currently in development: microwave superconducting platform interface to optical networks with electrical optical interconnects, optical platform with continuous qubit optical interfaces, photonic interconnected circuits, PICs. So quantum photonic space-time multiplexing. So parallel to time-space manipulation in global fiber optic communications, which is going to provide a time division, wave division multiplexing, standard quantum computing speed up, space accelerated by testing the states of 3D space superposition of inputs, optical quantum computing speed up, time acceleration by testing the permutations of gate order, superpositions of gate order and inputs. So while we are going for conclusion, so in delivering the quantum states, the fundamental concepts of quantum states and operator is going to play a major role. Quantum states are the building blocks of quantum mechanics. So where quantum mechanics, quantum physics, quantum chemistry, quantum machine learning is going to play an altogether major role in integrating all the platforms for development, while operators allows us to manipulate and measure these states. So understanding these concepts in little bit will helpful for us to navigate into the quantum world to understand what is going to really present for QML, and they are going to form the basis of further exploration into quantum dynamics as well. So thank you learners, thank you all.